Hello everyone, this is my ES308 independent lab, and I will be testing some 3D printed materials against some of the more classic engineering materials. As just a quick guide to what I'm going to go over on this presentation, I will be going over my objective, what I want to accomplish in the lab setup, and kind of generally how I'll be testing materials. I'll go over the results that I've got, including the error, which is pretty significant in some of the test samples. I'll ruminate on some of the sources that I think the error could come from, and then I'll draw some conclusions and talk about how I would improve the lab in the future. Okay, as an objective, I'm going to be testing 3 different 3D printed materials and comparing them to some of the more common materials we use in the engineering industry. They're all coming off the bamboo printers upstairs in the duckring building in the makerspace. So I've tried to keep that as consistent as I can. I'll be using the Instron tensile testing machine for this lab. I was unfortunately only able to get 3 materials to print correctly. I could not get PLA to print on the Bamboo Lab machines, which I have no idea why that is. But you can see the test strip dimensions here on the slide, as well as my error equation. R is just going to stand for the real value that I've either gotten from the 3D printing material website or found on an engineering materials properties table. And M is going to be the measured results. All these samples were tested until they failed on the machines, and all the data was recorded on the Instron software and then compiled in Excel to generate these graphs. First material I tested was PETG. It turned out to be the strongest material overall, and also one of the stiffest. It had a fairly small, for my testing samples, variation to the published material that you can see in the bottom, which I was able to find from the Matter Hackers website for the specific printer filament. It broke brittlely, and the break surface showed some severe delamination between the top, I'd say 50% of the layer lines, and so I think that's accounting for a lot of this error. The next material I tested was nylon. I was able to find the published values from an engineering properties table online. It's the only place I could find the Young's modulus and the ultimate strength in the same chart, and hopefully for the same material. I couldn't find anywhere that had values for the specific 3D printing filament that I used, and so a lot of this large error could be due to the differences inherent in normal nylon manufacture versus 3D printing. You're going to get less strength with 3D printing. Oddly enough, this had the lowest amount of layer delamination, had a very homogeneous structure at the breaking surface, and it broke brittly. It was also the least elastic polymer that I tested. It was the stiffest of any of the polymers I tested by a significant amount. Okay, ABS. I was able to find the specific filament data for this material as well, and the variations from the published numbers aren't too terribly severe. My Young's modulus is quite a bit lower, which just means I think that's due to the layer delaminations, which you saw again on this particular test strip. So I'm imagining it just didn't have the stiffness to get up near those correct numbers. But yeah, it broke brittly, shattered pretty severely at the end of the test, and was very middle of the road as far as its properties. Next are some comparative charts. Kind of shows the polymers I tested against wood, fiberglass, and 60 series aluminum, and you can see that the polymers stack up pretty well, especially the PETG, against your lighter woods and your fiberglasses, but they do poorly against aluminum, which is to be expected. I wasn't overly surprised by these results. As you saw in my results slides, there were some pretty significant errors compared to the published data on nylon especially, but also the 2 other filaments. I think the main source of that is this print layer delamination. I got some severe delaminations on those break surfaces, 50% plus of the area. I have no idea why. I'm assuming that it's due to the material storage conditions. I assume there was some water that got into the filament and caused it to lose its strength and delaminate as soon as it got away from the build plate and away from that hot surface. The machine testing or the machine resolution could also be a source of error, but given how reliable this machine is, I doubt that is any significant source compared to the other two variables. So given these tests, the 3D printed polymers that I tested are sufficient, I would say, to replace wood and composites in many small designs, especially those that aren't under a great deal of load or don't have the requirement to be overly stiff under that load. They can take a little bit of deflection. I would really like to redo this test at some point with a greater volume of samples. I would also like to control the sample quality better, whether that be a heated build environment or some different settings on the 3D printers or just some fresh filament. I would like to retest and see if I can get closer to those published values and reduce my error some. The only thing that really surprised me in this test was the PET sheet. I was not expecting it to perform better than the nylon in every area, but it most certainly did, and it still had the layer lamination problems, so I was very impressed by the strength of that PET sheet. Thank you for listening.